Hi everyone, I'm Yi. Today I'd like to present an elevator pitch about the paper Federated Learning with Fair Worker Selection, a multi-round submodular maximization approach. So federated learning is a machine learning technique that enables edge devices like smartphones to collaboratively train models without sending sensitive data to the cloud. Instead of uploading raw data, devices download a model, improve it with local data, and send only encrypt updates back to the cloud. This preserves privacy and security. An example of federated learning in action is Gboard's next word prediction feature. It uses federated learning to train an LSTM model across devices by sending model weights to a subset of phones, which updates them based on local data, and the server averages these updates to improve the model. However, federated learning faces a fairness challenge. Not all devices contribute equally. Um, since the data is inherently non-uniform, different users have different typing styles, habits, and languages. If the training process favors devices that are online more often or have more data, the model can be biased towards these users. It can happen that works well for Gen Z users who type certain phrases frequently, but poorly for older users with different patterns. Even if overall accuracy looks good, individual users may experience poor performance. To make the model performance more fair, we treat fairness as a constraint in worker selection. Each device is assigned a minimum participation threshold. This helps ensure that underrepresented users still have a voice in shaping the model. The worker selection process is framed as a combinational optimization problem where we maximize the overall model utility while satisfying fairness requirements. So the problem of worker selection with long-term fairness is essentially a linear programming problem. So this is an NP-hard problem that could only be approximated. To do so, the paper first proposes a continuous greedy algorithm called FairCG. This algorithm searches for the optimal utility in the continuous space within the fairness and max worker constraints. It faced three major challenges. First, our setup doesn't perfectly fit the requirement of continuous greedy algorithm. So this turned out to be fine as it is proved that the feasibility of the result. So the authors further ensured the feasibility of every step with a revised version of FairCG. Second, the solution leaves a continuous space, but in practice, we need a concrete selection. It is solved with a rounding algorithm to turn the result into a concrete selection strategy. Third, with different forms of objective, it's hard to know how accurate the approximation is. But the numerical analysis shows the approximation ratio is actually great. But there's one more thing to take care of. All of this only works in the long term, assuming we have infinite rounds. But what if we want fairness early, let's say just in the first 100 rounds? The paper proposes another algorithm called FairDG to guarantee short-term fairness. The key idea is originated from classic discrete greedy algorithm, but instead of always selecting workers based purely on marginal utility, FairDG first checks if any workers are behind in their fair share of selections. If the number of such workers is less than the number we need to select in the current round, we simply choose all of them and fill the remaining spots by utility. So if there are more, we select those with larger stats. So this approach ensures that each worker's number of selections stay as close as possible to their fair share, with difference never exceeding 1. Comparing to fair CG, it has lower time complexity. In terms of the performance of these three algorithms, so fair DG achieves almost the same average utility as fair DGs, yeah, with a slight decrease. Both algorithms, they satisfy the fairness constraints, but fair DG takes fewer rounds to reach fairness requirements. The paper also tested the impact of fairness requirement on the time average utility. The results showed increasing the fairness requirements doesn't negatively affect the time average utility. That's all of the presentation. Thank you for listening.